So let's start. First of all, thank you all for joining this session. It's the first webinar we have on security, and the idea behind this is to have to share with you, with the community, some topics which are in development and happening in the Keysight ATI group. ATI stands for Application and Threat Intelligence, and practically is the security team inside Keysight. In Romania, we have a good presence, about 30 to 40 people, split it between projects. And we thought it's a good idea to share with you, with the community, some of the topics which are happening and might be interesting for you all. This is the first session. Most probably we will have some others as well. But in the same time, apart the Keysight webinar, you should also look for the Keysight Connect sessions, which are held every 3 months, so in every quarter, on not necessarily on security topics, but on some other interesting engineering topics coming from Keysight, from our development. So with this, I will hand it over to Radu for the first topic. I encourage you to ask a question, and we'll take the Q&A session at the end. I'll read the chat and the questions, so we'll discuss about them at the end. Radu, please share your screen, and let's go ahead with the first topic. Thank you.
Thank you, Florian, for the introduction. Hello, everyone. I hope that you're able to hear me clearly. My name is again Radu-Emanuel Chiscariu, and I'm a security research engineer at Keysight Application Threat Intelligence team. And my presentation for you is about dynamic instrumentation using the Frida binary instrumentation framework. My presentation is going to be organized as follows. We will begin with a couple of general ideas about what binary instrumentation is, how it works, and how it can be conducted. Then we'll delve into Frida, its inner workings, and we will discuss about its components and how are we able to do instrumentation with it. Then we will present a couple of examples that will showcase its powers and how it can be used for a security-minded person. So dynamic instrumentation means it's a technique that we can use in order to obtain information about a process during its execution. That is dynamic what stands for. And what kind of information can we gain? We can infer information about what kind of CPU instruction have been executed or certain syscalls. We're not trying to completely modify the behavior of the application here, of the process. We are only trying to insert certain things that will allow us to collect information about how the process behaves, allowing us to better understand what's going on there. Why would we want to do it? To do this for well, for a developer, it's extremely helpful because it can monitor the application, the target application, in order to gain insight about the coverage or do some kind of diagnosis. Also, it's very useful when you're doing benchmarking in order to determine its performance and solve some issues that can arise and in this perspective. But it's also extremely helpful for security person, because we can use binary instrumentation to study the behavior of the application that do not have a source code in order to maybe determine and find vulnerabilities, or maybe even study a malware sample and understand how that operates. Using a binary instrumentation framework, we can basically do all kinds of stuff, or fuzzing, taint analysis, or reverse engineering. But how does this instrumentation thing work? Well, there are a couple of methods that allow us to do instrumentation on a target application. The most common one and the easiest to understand is, of course, the trap mode instrumentation. What that means is basically we insert a CPU instruction that helps the execution of the process. It's basically what an debugger does. So every time you debug an application, you are doing actually instrumentation. The debugger will replace the instruction that we want with a int3, for example. And when that instruction is to be instructed, then the execution will halt, and the control will be transferred, will be relinquished to the debugger. And in this way, the debugger can present us information about the registry state of memory, and so on and so forth. This is the easiest, as I said, but we have to keep in mind that it's very expensive, because if you're doing a lot of traps, the context switch between the user space and the kernel space will cause a lot of latency. So if you're trying to use it, we scale it and use it multiple times for multiple blocks that we want to instrument, then we're going to have a very big overhead. Another more interesting way to do instrumentation, it's based on JIT-Recompilation. As the name says, we're basically using JIT in order to recompilation in order to monitor a certain process. And how is that done? Well, if we have a certain basic block that we want to understand, if we want to analyze, we will take it, we will transform it into an intermediate representation, and then we will add the instrumentation code that we want to use in order to study that basic block, and we're using the JIT compiler in order to recompile the whole thing. This way of instrumentation will keep a reference to the original basic block, the unmodified one, in memory, and it will create multiple copies of the modified basic blocks in memory. And what that means is that it can also have a very big overhead, because it has to operate with all that copies. And it have to recompile on demand each basic block that we want to instrument. So it can cause a really big overhead. We're talking about maybe 50 times slower execution than a normal execution. Another way to do instrumentation, maybe the coolest one, is trampoline-based instrumentation. It's extremely easy to understand. The idea is to basically modify change the execution, and you practically provide the jump to a block that you create yourself, and then you return back to the original block. So you're not modifying the whole block, you're just redirecting the execution to something to the instrumentation code that you provide yourself, and then return to original one. Intuitively, this can have a smaller overhead. It's quite fast. Actually, it's so much faster than the other ways of doing instrumentation. But it has a couple of limitations, and here we discuss these are caused by the fact that since we're in the same stack context, some of the registries will be clobbered if we're not doing the instrumentation right. So we'll have to return the registers to the original states after we finished using them for whatever kind of instrumentation that we want to create. Also, there can be some other issues if we are operating on a instruction set architecture that is not aligned, because doing this kind of instrumentation in that situation will, if not done carefully, will practically overwrite certain instruction, and will basically break the process and will change its behavior, and we do not want that when you're doing instrumentation. Okay, so what kind of frameworks are out there? I'm not going to insist too much on it. These are the most common and used. Pin and DynamoRail are the oldest, and they're the most used. With DynamoRail, I'm a little bit more familiar because this binary instrumentation framework, it's used in order to do fuzzing on Windows. WinAFL, if you heard about it, uses DynamoRail in order to gain information about basic block coverage, and it uses that in order to do fuzzing and create better samples that have a larger coverage. And about Frida, we're going to discuss in depth a little bit more later. So the usual steps when using this kind of binary instrumentation framework is to write a harness. It's a tool that makes use of the framework API in order to inject a certain code that we in the process that we want to instrument. Then we will compile that tool as a shared library, and using a tool that the framework provides, we inject that piece of code that we written into the process, and that can be done in multiple ways. We can either add it as a probe. It's similar with how a debugger operates. It will, and the other way is to practically run the whole binary within the framework of within the instrumentation framework that is called binary translation. So what is Frida? Well, except the fact that it's a well-renowned painter artist, it's also a binary instrumentation framework that became very popular on the mobile mobile community. It's completely open source. It's highly scriptable, and it can work and it can do instrumentation on a whole lot of platforms, whether it's Linux, Windows, Android. It can instrument everything. And it has a very good documentation and a lot of examples that you can start working with. It's very easy to install, and after installation, you can start using it with certain command line tools provided. So we'll go through a couple of them just to see how Frida operates and what it can do. One tool is Frida CLI, which operates in a REPL manner. You are basically presented with a shell in which you can invoke all the Frida API in order to do the operation needed. Here is an example of that. For example, let's say that we want to see all the modules that the Google Chrome browser loads when the browser process starts, and what we will do is we will determine the parent process ID of the Google Chrome, and then we will simply invoke from a command line the tool Frida, having as argument the process ID. After we do that, we're presented with that REPL that I was talking about, in which we can use the enumerate modules API pertaining to the process class, and this will basically dump us all the modules that the Google Chrome loaded during this execution. As you can see, it's extremely easy, and the API is quite friendly. Another very useful tool is Frida Trace. Let's see how can we use it. For example, let's say that we are interested in seeing how what kind of Windows APIs will be used when we are trying to save a file on disk. So we were trying to do this kind of operation. We just want to see what kind of functions are invoked and what kind of parameters those functions have. When we're doing, let's say we'll open a Notepad process, and then we will identify its process ID. And after then, we can use Frida trace in order to trace all the APIs, Windows APIs in this case, that this process can use. So what that will do, we'll go through all the loaded modules within that process, and we will identify the exported functions that that pass this regex here. So we'll basically identify all the exported functions that have this name. As you can see within the Notepad process, there are about 26 functions. And for each of these functions, it will create a JavaScript file. Let's see, and it will begin tracing them. So let's see what actually is within that, within a JS file. They're very straightforward. We have basically two callback functions here. We have defined on enter and one leave. So what are these? They are JavaScript functions that are going to be executed when the API that we're trying to trace is invoked at runtime within that process. So each time that function is called, the execution is going to be redirected to this callback function on enter, and we will be presented on the on our command prompt with this kind of message. There is also the onLeave function, which does essentially the same thing, but when the function is going to terminate its execution. Let's see that in action. So when we're trying to save the file that we created in Notepad on disk, as we can see in our console, we are prompted with those messages that we've seen earlier in the JavaScript. And each time that function is called at runtime, if we're trying to save the file multiple times, we're going to be presented with this kind of messages. So it's very easy to trace execution depending on what we need to do. Okay, so let's extend that script that was created automatically by Frida by not only finding whether that function was executed, but also let's see its arguments. So I want to see what kind of arguments does the create file API, Windows API, have when it's executed. In order to do that, we have to go to the Microsoft documentation and find the API's prototype, and based on that, we can create further log messages in order to prompt us with the arguments. As we can see, the onEnter function, it also contains the arguments of the function that is called during runtime. The first argument is a string, so we're expecting that to be a pointer, and we can print it to the console by using the read UTF-16 string Frida API call. The other two are just D words, so we're expecting them to find them in memory as it is. So we do not have to do any other things except just print them, and that's it. So let's see if the arguments are presented correctly by the Frida as we wanted them to do. We also introduced on leave a simple log that we're going to use to delimitate better and see what's going on. And sure enough, Frida does its job. And as we can see, we are presented with the function arguments when we're trying to save a file, and we can understand what's going on and inspect each argument and see if they are correctly presented. Of course, the first argument is the file that we created on disk. As we can see, it's the exact same file with the name that we created. But the other two, we're not sure if they're okay. Maybe just read random stuff from memory. In order to make sure that everything is all right, we can consult Microsoft documentation, and sure enough, those are flags that they are used as in order to define specific access to the file or what privileges, share privileges that file going to have. In this case, the argument is going to be OXC, which means a generic read-write. So it's conform with the documentation. And the last one defines the file share read, which is the value, the exact value as in the documentation. So everything is fine. introspected the process correctly, this API, and it works as it should. And now we know how what happens when you're trying to save a file on Windows. But what if I would tell you that you can do this whole thing automatically without having to inspect to go through Microsoft documentation and just implement everything on your own? Well, Microsoft released their SDK publicly, and now with a little bit of scripting, you can just get the function prototypes and basically create your own API tracer. You would have to point for each exported function in each DLL, its arguments and types of arguments. And you can basically inspect any kind of process in Windows, and you can see on real time what happens when that process is executing. So pretty cool, pretty powerful framework, I will say. So how this magic happens? We're going to make a high overview of how this works. Basically, the Frida core component will load the Google V8 JavaScript engine within the process memory. And Frida core, through the Frida agent, is going to dynamically hook the functions that we're trying to instrument, and it will redirect execution to the JavaScript files that we are going to define ourselves. As we saw earlier, those JavaScript that were created automatically. So each time a function of interest, so when we will define that function, the execution is going to be redirected to the V8 engine, and then it will execute the JavaScript file within the process that we're trying to analyze. How does the actual instrumentation happen? Well, there are two main components that Frida has in order to do that. The one is called interceptor, and what that does, that allows you to do is either intercept calls to a function, as we saw earlier, or it can even replace implementation, and you're doing that based on one-ter and one-leaf functions that we can control and implement, as we saw earlier. If a function is very hot, meaning it has a lot of executions, it executes multiple times during process runtime, you can even provide the C implementation to make everything so much faster, rather than providing a JavaScript implementation. The other component that Frida uses is called Stalker, and what that does, it's looking on a certain thread, and it inspects, and it's looking what kind of instructions are executed, let's say, and based on that, it returns a set of events. And the kind of events that are currently supported by Frida are the following: the call instructions, the return, we can also return all the instructions, but as you can imagine, that it can be extremely slow, and it can also return the blocks that were executed, like their address in their virtual address, and the compile. Those two can be used if you're trying to determine the coverage of a certain function or a certain component within the process of interest. So pretty cool stuff. It's pretty flexible, I would say. Beyond the fact that we can use those tools, as we saw earlier, we can also create them ourselves based on the bindings that Frida Frida provides. So you can create your own scripts in Python or Swift or Node.js, and what you have to do is basically you would have to attach to the process, as we saw earlier, but you can do that programmatically. Then you would have to write a JS script that defines what kinds of instrumentation operation are done. And you would use that, and you would use Frida API, you would use a stalker and interceptor, as we saw earlier. After we define that script, then we just have to inject it into memory, load it, and after Frida provides the information that we need, the instrumentation operation, then we just have to decide what to do with it. And in order to exemplify that, I made a demo for you. the demo is going. We will in this demo basically what we'll do is we're going to launch a process, and we'll trying to do some kind of instrumentation to see what's going on within it. So let's say that this is a binary that we do not have the source code for it, and the binary behaves in this manner. It will take a file as an argument, and then it will wait for 3 seconds. That can be a representation for some kind of a network operation, and after that wait, it will simply parse the file, and depending upon what file it is provided as an argument, it will behave in a different manner. So the important thing here is not what is within these files, it's just the fact that for different files, the program will have a different behavior. So for the first demo, what we're trying to do is we will hook to the method that does the file reading, and we will monitor its execution. And then for the second demo, we're trying to do something more interesting. We will try to alter the function arguments. And even more than that, we saw that we have the binary waits 3 seconds before parsing the actual file. So what we're trying to do in the second demo is we will change the behavior of that function. It will make it to just jump to the file processing without incurring that 3 seconds penalty. So let's see that in practice. Okay, can you see my screen? I hope that you do. So here we are in the, let's see that binary executing again. As we saw earlier, as we said, that there will be a 3 second wait before the file is parsed, and the same with the second file. It's just that we'll have a different output based on the file, what is the content of the file. Okay, so let's try to use Frida API, the Python bindings in order to basically instrument the function that does the parsing and see what kind of what is happening there. Okay, so for the first thing, we will spawn the process as we saw earlier, but we will spawn it programmatically, having the file as argument. Then we will create a Frida session when we'll attach it to that process ID. Then we will load a JS file as we saw earlier in the examples with Notepad, and we create that script in memory. Here, basically, the Google VOpt engine is going to be loaded, and when a certain function is going to be hooked, then the execution is going to be redirected to VOpt, which is going to execute our JavaScript file. Okay, so we need a way to find the function that we're going to instrument. And as the function is not exported, we will have to find its in-memory address by identifying the address of the module that is that has that function, and providing and summing it with the offset of the function. And we can determine easily this offset by inspecting the process in IDA, let's say. So in our case, the offset of the function that is of interest for us, the function that reads the file, is the last significant 4 bits, so it's 1110. Okay, so this is the offset that we're providing at here, and then we're calling a function defined in the script, which is called instrument target. Moving on to the Frida helper.js, the script that we did ourselves, the instrument target is going to do the following. Is going to, sorry? Was that a question, or should I continue? Okay. Okay, I will continue, I guess. So we will determine the function address by adding the base address of the module that is containing the function with the offset, and then we'll do we will use the interceptor in which we will define one enter callback, as we saw in the example earlier, and we will just print a message to the console that says that, okay, Frida managed to identify the function of interest correctly, and it has a certain argument. So when we're going to execute that process, we should see this message correctly if we identify the function correctly, and it is going to print something like this. Okay, and also we're going to measure the time of the function, just to make sure that those 3 seconds that are in the that are taking place in the binary are actually happening. Okay. Okay, so let's execute the first one. See if everything works out okay. As you can see here, the Frida script that we created, the JavaScript file that we created, was loaded into the process memory. Then Frida correctly identified the address of the function that we wanted to, and sure enough, also we can see that the argument that the function was called and the argument of that function was indeed this one that we provided in the at the beginning when we launched the process. So extremely easy to instrument. As we see, we just have to define the intercept.attach operation, and we can just start dumping information about the runtime behavior of the process of interest. In the second demo, as I said, what we're trying to do is not only monitor the execution of the function of interest, but also we want to alter its arguments, and moreover, we're trying to actually change the implementation without having access to the source code, and we want to do that in order to not have those 3-second wait that are happening each time we're running the process. So in the second demo, let's see, we'll do something similar at the beginning. We will again spawn the process, having the first file as argument. Then we will create a session. We'll load the JS script that we created. And then we will execute the function, which is called instrument target, with the same function that did the same thing. It will just print this debugging information. But as I said, we want to change the argument of this function, and we will define the new argument that the function is going to take, the one that we want to. So in order to change its behavior, then we will execute this method having the new file that we want as argument. This execute method is again implemented here in JavaScript. So in order to change the parameters of the function at runtime, we have to allocate some memory that is going to keep the actual arguments. The first one is just a string; we do not care about it. But the second one is a string. But the first one is the actual file that we defined here. And we are going to use the Frida API called native function, in which we will hook the method ourselves. And then we will provide a pointer to the function of interest, its prototype, and we will call it ourselves here with the new arguments. Okay, let's see that if that it's actually happening. As you can see, this time when the execution took place, even though we provided the first file as argument, because we changed this behavior and we made it execute another file, the function is executed with our argument, and the behavior changed. But again, we have this 3-second wait, and we want that not to happen. So what we're going to do next is to find the function that incurs that performance penalty, the 3 seconds, and we will actually modify its implementation. And how you do it? Well, you can do it pretty easily. Again, we implement a couple of JavaScript. We will find the address of the function similarly by adding it to the base address of the module. And then we will use the interceptor that replaces Frida API. And the thing that we are going to do is simply return and not wait those 3 seconds. As we can see, in this case, we replaced the implementation with the JavaScript implementation that is going to be, again, that is going to happen via the Google V8 engine that is loaded at process runtime. Okay, so if you run it again, just to make everything clearly. In the first part of the demo, again, the download lasted for 3 seconds message appear. And we also measuring the time, we can see that 3 seconds, the 3 seconds wait has happening. But the second time when we change the method behavior, it will simply return without going through that function. And of course, just to make that sure that it's happening as we wanted, measuring the time, we can see that is definitely a difference, and those 3 seconds wait didn't take place, which is pretty cool. We basically, without having access to the code of that binary, we simply modify this behavior at runtime. Okay. So what else can we do with Frida beyond this? Like it cannot do enough. Well, one other thing that we can do is we can bypass SSL pinning. As you might know, this is a form of protection that that certain mobile application uses. Well, not only mobile, but in this case, we are going to talk about in the context of mobile protection. So SSL pinning means means that when an application executes, let's say like Waze, it will connect to a remote API in order to do the operation that we needed to. And because that operation takes place securely, in order to that operation take place securely, the whole exchange between the application and the API has to be made encrypted. And how that works is the remote API is going to provide the application, the mobile application, a certificate, and that certificate will define whether the mobile application actually talks with the API and that API is not impersonated. So what happens if we'll try to interpose? Let's say we're trying to use burp suit in order to see how the application talks with the API. As you might know, burp has its own self-signed certificates. But if you're trying to do that with an application that that implements SSL pinning, the certificate presented by the burp suit is not going to be accepted because it's not consistent with the certificate that is pinned within the application. So our attempt to interpose between the application and the API is not going to work. But turns out that we can use Frida in order to bypass that, and there are multiple examples all over the internet which presents you with the whole necessary steps in order to do it. And in this way, you can do proxy testing without any issues, because Frida will basically hook the function that is responsible for verifying the certificate, and you can define your own certificate and present it to the application like it's as being a trusted certificate. As I've said earlier, Frida provides a couple of examples, a couple of scripts that were used by the community in their hacking attempts or reverse engineering attempts, and all of those are that the people wanted to share with the community are presented on Frida Codeshare, and you can find them and study and get better acquainted with the whole framework. Here is a couple of links that I provided for you if you want to get started with Frida. There's the documentation very well put, the code share, and a couple of Frida scripts on GitHub that you can get started with. This was my presentation. I hope that you enjoyed, and I'm glad to answer any question that you have. Thank you.
Thank you. Thank you very much, Radu. Any questions on Radu's slides on what he presented? If you have any questions, you can put on the Q&A section or directly in the chat, and we can read them. In the meantime, Radu, maybe you can give to the audience how we are using Frida internally and what is, I don't know, or maybe what are the plans you have with it?
Can you hear me?
Yes.
Okay, so we are using Frida in order to better understand how certain applications work. One of the products that we are developing is called the breaking point system, and that product has a component with concern itself with generating traffic for different, which we are calling flows or super flows. And in order to do it, we have to analyze a lot of traffic. Sometimes we cannot. Sometimes the traffic generated between for an application is encrypted. I mean, most of the times it's encrypted. So we'd have to use a form of bypass SSL pinning. Let's say if you want to study a mobile application. So that's one way that Frida is used, as I said. One other way is we're exploring a couple of different methods in order to do fuzzing on application of interest and determine vulnerabilities. And we're, as I said, we're exploring a couple of different ways to do it. And one of this is using Frida. As we've seen in the examples, we can extremely easily hook to a function of interest, and we can call it repeatedly, and we can fuzz that API using Frida in that manner.
Okay, thank you. I see no questions on the chat or on the Q&A section. So probably with this we can move to the next presentation. Thank you very much, Radu. Very nice presentation.
If I might also add, sorry for the interruption. If you have any question, you can find me on email or on Twitter, and you can post them there without any problem. So thank you again for listening to the presentation.
In the meantime, we have a question. Is there any shortcoming compared to paid version of DBI? Do you know?
Sorry, what was the question?
Is there any shortcoming compared to paid version of DBI?
Most of the frameworks that I've used are free. DynamoRay is free, as you can use it without any form of payment. Pin is also free. Frida is completely open source. There might be some other cool features that paid DBI uses. For example, it might have symbolic execution or something, but for the things that I've needed, it really raised to the expectations, let's say.
Okay, hope this answers your question. Any others? Okay. Okay, thank you, Radu. Let's switch to the next one. Sebi, you can share the screen. As a brief introduction, Sebi will talk a bit here about some issues we found in the serialization and deserialization on web application servers. This is mainly focused on the Oracle Weblogic, and we didn't selected for any reason, but only just to showcase what are the possible issues you might encounter from security perspective with such web application. Of course, this can be applicable as well for other web applications, so it's not necessarily limited to that, but it's a use case Sebi will detail and what are his findings. Sebi, go ahead.
Hello. Can anybody hear me?
Yes, we can hear you.
Okay, excellent. So, hello, my name is Radu-Emanuel Chiscariu. I am working as a security research engineer within IXIA's Application Threat Intelligence Research Center, like Radu. Today, or in this session, I'm going to tell an introductory story about the most successful deserialization vulnerabilities and exploits that target Oracle Weblogic service. Basically, we didn't find these vulnerabilities. This is not a personal research. This is just a summary based on non-sec 404 group research around Oracle Weblogic XML deserialization flaws. Along WebLogic deserialization bugs and fixes, I am gonna share with you some general information about serialization and deserialization aspects. Okay, so a little bit of context here. A threat intelligence platform relies on the versatility of its data sources. Basically, internal honeypot events or external malware feeds or external URL feeds is the input data for each threat intelligence platform. So analyzing our HTTP honeypot events, an interesting group of requests appeared. And I said, okay, let's analyze them and see what we can get there. So basically it is, or what I saw was a simple HTTP unauthenticated post request for a WebLogic specific endpoint with SOAP enveloped body with process builder keyword init, indicating a remote command execution type. And as post-exploitation payload, most of them try to download and execute different types of coin miners. Basically, as post-exploitation, every event had this payload coin mining. Further on, why Oracle Weblogic? So Oracle Weblogic is an enterprise, a world-leading enterprise Java application server. Well, there are other solutions like Apache Struts or Apache Tomcat around Java application servers, but when it comes to enterprise, Java is the world's leading solution, let's say. So when enterprise is in title, means enterprise grade resources are available, or enterprise grade resources are there. Zoomeye.org is a cybersecurity search engine managed by non-sec 404 research group, and this search engine says there are a fairly large number of Oracle WebLogic instances all over the world. Why deserialization? So first of all, we need to know what is serialization in order to say what is this serialization. So serialization is the process of translating object states and data structures into a format that can be stored or transmitted and then reconstructed. Basically, you can, using serialization and deserialization, you can transfer data or you can do effort balance between client session or client instance or server and a server instance. And deserialization is the reverse process. Of course, the format, the serialization format can be a non-readable byte array or readable formats as XML, JSON, or any other readable formats. And when it comes to vulnerabilities, serialization vulnerabilities often lead to reliable code execution and are generally hard to patch. Okay, and then why coin miners? Coin mining method is coin mining method is the safest way to get rich. Let's say, if you can take over or you can borrow so enterprise resources, that means profit. And if there are multiple hosts that expose enterprise resources, there are, a larger profit. So this little article says says a story about, says a successful story about these vulnerabilities and exploitation of it. It's a 2019 old article, but it stands as a proof. Okay, so further on, the story begins with CV 2017 10271, and that CNVD ID. CNVD stands for China National Vulnerability Database. So straightforward was an unauthenticated POS request against a VLS VSAT subcomponent, which is a WebLogic security subcomponent, but any other subcomponent that calls the built-in Java deserialization method, which is XML decoder, can be a target for this attack vector. It affected most version, and actually the invocation of class was so using a void tag, the Java line process builder class invocation was made. Okay. The fix was on October 2017, and the fix was captured in a patch pack, the October 2017 pack, and it basically it adds a work context filter in document XML handler, and it filters basically new object method tags completely, and void tag accepted only index attribute. Unfortunately, this fix was not included in downloadable kits, as NodeSec Group said in this article, and this changed a little bit the story further on. In 2019, a vulnerability that bypasses the validation step from 2017 was brought to light. It affected some version, and most POC targeted VLS, VSAT, and VLS ASIC subcomponents were its target. These subcomponents are stuck in WebLogic, but everything that uses XML decoder in its code can be a target. Everything as in a custom web application that comes on top of Oracle Weblogic. This time, class tag was used to invoke a second handler that bypasses the initial validation mechanism. Notice the two Java tags. Second one just starts an XML segment similar to the 2017 bug. But this can be possible with another handler invocation, that slf4j.x event data is the XML handler that bypasses the validation, the work context or document handler validation step. Also, VCA action and VCA relates to tags are part of the bypass mechanism. And the fact that the 2017 fix was not included in downloadable installation kits affected the collective research, and a lot of POC that advertised CV 2019-2725 with 2017 payload without bypass vector appeared. So basically, if you are in a CTF scenario or if you are having an assignment around Oracle Weblogic, be aware of the POC that use void class without the bypass. Okay, the fix was captured in an out-of-band patch that updated the validation blacklist. So class tab was completely filtered, and the bypass vector cannot be used anymore. Couple of days later, another bypass appeared. Some versions are affected, but same subcomponents and same XML decoder method is targeted. This time, array and byte tags are used to deliver a non-readable serialized object created with ISO serial. And this method depends on the JDK version used in the application server. This POC is not a plug-and-play script. It's just a description of how attack vector looks, and another technical details about this attack vector. The fix was also an out-of-band patch just a couple of days later, and the byte tag was completely filtered. So this method is obsolete. Okay. Further on, this is a simple timeline of the events around XML decoder deserialization method. Just notice periods between vulnerability disclosure, fixes, and then bypass method. So basically, in just a couple of weeks, a bypass appeared, a fix, and then another bypass. It means the bug was pretty serious. In this GitHub repo, you can find a WebLogic scanner that actively scans for XML deserialization flows, and not only. this scanner is pretty intrusive and is not recommended to be used in production environments. Active scans means it actively tries to exploit the WebLogic instance and report the vulnerability. Further on, I'm going to list the latest deserialization vulnerabilities around WebLogic Server, and these vulnerabilities are not HTTP deliverable. They rely on IOP and T3 RMI protocols. This one, 2551, is practically GNDI lookup. Basically, it query a remote serialized malicious object hosted by a rogue RMI server. Some technical information you can find on that on Medium blog, along with the POC and the patch. 2022-555 and 2883 are remote code vulnerabilities that target coherence library and deliver a rogue serialized object through T3 RMI protocol. So 2883 is just a bypass of the fix for 255. They are related. Also, technical information. You can find technical information on the ZDI links, along with the source code for POCs and patches. So what's next? At the end of May, China National Vulnerability Database raised some critical alerts that indicate the existence of 0 days, and these are undisclosed by Chinese researchers. Maybe after the patch is released, we will see CVs and public POC for these vulnerabilities. Of course, the first one is not related to serialization, deserialization, but it has a 10 impact score. And the second and third one might be related to serialization or deserialization flaws, vulnerabilities. This is the timeline of vulnerability disclosure and fixes, and CNVD alerts. Notice that this is just a couple of weeks from this date, the current time. In conclusion, due to the fact that deserialization method offers a great flexibility in transferring and storing data, flexibility usually increases the risk. And deserialization bugs are pretty hard to fix. The bypass method appear all the time. I don't know, maybe a denial methodology and a whitelist of the required classes might be a solution, but this solution is just a cut from flexibility. And also, Oracle Weblogic and any other Java application servers deal with a lot of deserialization related risk. Solution could be to implement a network-based security control, like a firewall, practically every protocol that is not used should be blocked by the firewall. Another solution could be an IDS or IPS that detect or reject session based on signatures, but this comes with a performance cost. Another solution could be Ixia's threat armor product. This is a session filter based on an updated IP blacklist, and it works without a performance impact. Of course, it does not replace a firewall, but it can be set as an additional layer of defense in front of firewall or behind. That was about it. Thank you so much for your time. And if you have any questions, go ahead. I will try my best to answer.
Yeah, thank you, Sebi. Again, if you have questions, you have the Q&A panel or the chat window, so we can answer. I think what needs to be said here is that these CVs, which were studied and analyzed by Sebi, are included or will be included in some of our products. Sebi, I think the first one is the threat armor, right? Some of them are already.
Yes, they are already in the collecting mechanism of our threat platform, threat intelligence platform.
Yeah.
So basically, we collect events that are related to XML deserialization vulnerabilities.
Okay. I see no questions coming. So if there is nothing to be asked here, I think that's all. Thank you very much, Sebi. Thank you all for attending. We'll try to have other similar sessions, and we'll advertise them via usual channels. So yeah, thank you for attending, and see you next time.